Good afternoon. So first, I would like to thank SAPA for giving me the chance to give the seminar. And my speech will mainly on how AI synthesis planning tool like ChemAIRS will accelerate the preclinical drug discovery. So it is well known that to get one approved drug, hundreds of new molecules need to be synthesized. And if we also calculate the failed projects, which could be 10 times of the successful ones, thousands of new molecule entities need to be synthesized, and it surely will take a long time and cost a lot. So organic synthesis is still a rate limiting step in drug discovery projects. To increase the synthesis efficiency, a lot of computer-aided synthesis planning tools have already been commercialized and have already been used by big pharmaceutical companies. You may have heard of some of them. It will help chemists to find quickly the shortest and most feasible routes, which will surely speed up the design, making, test, analyze cycle. And now in the market, there are currently 3 different approaches to achieve synthesis planning. The first approach is purely data-driven method, which use automation rule generation, and it is easy to implement. You just put data and it will train a model. But this kind of approach faces some difficulties. For example, there are a lot of different chemical reaction types, maybe nearly 1 million of reaction types. And there are sample reactions like protection or deprotection. There are a lot of data of these simple reactions. But for some rare reaction types, there are only a few data, which will cause problem because it is not enough for deep learning. And another problem is the lack of interpretability. As the deep learning is a black box, you can see the input and output, but the logic inside is unknown. So maybe the logic learned by the algorithm is totally wrong. It's possible. So we could not improve the system easily because we don't know the logic, and we have no other tool to change this logic. It's learned by itself. So this is a big problem for deep learning. And here, a second approach is to have human experts to write a lot of reaction rules, which is a very tedious work. And human experience is often biased and even contradictory between them and also with real data. And this approach is called expert rule-based approach. It's used by, for example, Chemical.AI or Zhihua, actually. And this will become a bottleneck problem, which prevents the system to become much better. And our approach is quite different. We use data learning aided by chemistry knowledge, which means we have the advantage of both approaches, and we do not have the problem of interpretability problem, and also the accuracy is quite good. All routes in our algorithm are learned from data automatically, but it's not a black box, it's a red box. And we use expert knowledge to adjust the algorithm to tell it how to learn from data, how to extract rules. So the system is totally interpretable and it is easy to do reaction condition optimization work. And now our platform ChemAIRS have become the leader in the market. We have collaborated with big pharmaceutical companies in US and in Europe. And we also have thousands of online users, which are small company users and also academic users. So after the introduction of the background, I will start to introduce ChemAIRS system. First, I will show you some evaluation result of ChemAIRS. And this was a published result by Wuxi in CES, like online conference. Wuxi have evaluated 9 different retrosynthesis systems with 60 diverse targets. And here we can see ChemAIRS got the highest score and much better than most of other systems. And we have also organized an interesting human versus AI competition internally. We have 16 chemists with average 10 years of experience have participated, and they all allowed to use other literature database tools. Both sides designed synthesis route for 22 different targets, and then 6 principal chemists will score the routes by feasibility and number of steps and other criteria. So in terms of time cost of synthesis route design, AI we see is largely faster than human, with 8.7 minutes in average. And the average design time for chemists is 1.5 hours, nearly 10 times more than the AI system. And it need to also mention that chemists only design one route, but ChemAIRS can give dozens of routes with different synthesis strategy. And the most important score is about route feasibility, which is often not quite good in other systems. In the competition, in 10 cases out of 22 molecules, AI route feasibility scores were higher than chemist score. In 3 cases, AI score are equivalent of chemist, and the average score of AI is 8.477, just slightly higher than the score of human chemist. So we can say the system is quite equivalent to experienced human chemist. When we look into the diversity of routes, ChemAIRS provide 2 to 6 different synthesis strategies, including different key steps and key intermediates, which can help chemists to quickly find a better strategy. It's very useful to chemists. Here is an example of route. The route above is designed by chemists, and the route below is ChemAIRS route. We can see the key ring close strategy. Chemists used 3 steps to close the ring, and AI used only 1 step, which made this route shorter than the chemist route. In another example, you can see the strategy step here is how to construct the 7-member fused ring. The chemist chose to close the ring by Freud-Craft reaction, but which could cause regional selectivity problem here. It can close in 2 sides. And ChemAIRS used a condensation reaction between 2 alcohol groups, which do not have this selectivity problem. So in some cases, Chemical.AI can prevent wrong route or a reaction which could fail. So then I will try to show you how ChemAIRS can help medicinal and process chemists in their work. ChemAIRS have several key features. First, it's very fast. It's capable to generate routes from seconds to several minutes. So this can accelerate the design speed of routes, save a lot of time for chemists. And also, it can overcome difficult targets. which means if you have a molecule structure, it's very complex, or chemists don't know how to synthesize it. You can try ChemAIRS, and it often gives you a lot of new ideas to make this structure. It also gave you a diversity of ideas, which can, when one route didn't work, you can try another. So it's very useful. Of course, I just said it can prevent failed reactions. So some reactions, the human, if it's not quite experienced, it won't know. But with failed reaction data, ChemAIRS can predict some reaction which could fail. And also, we use ChemAIRS to optimize reaction conditions. If the yield is not good or if it doesn't work, you can always find a lot of different strategies to do the reaction. And another very important thing is we can integrate internal ERN data and the building block data into the system. And this will make better use of the internal data, and the commercial available building blocks and price information can help chemists to find the most economic route and also shorten the route. And the system is very easy to use. First, you can just draw the molecule in the Marvin.js panel, which is quite familiar with most chemists. Or you can just paste a smells or case number in the text box, and you click, when you have the structure, you click search button. And during the search, you can see the number of the routes increase quite fast. And no need to wait the task to end. You just click the number, you can see all the routes already found. And the routes are ordered by feasibility score by default. And reported molecule or reactions are marked by green color. Predicted routes or reactions or molecules are in purple color. You can also use, you can also see ERN mark if the reaction comes from your ERN data. So firstly, ChemAIRS can show very similar capability of route design with experienced chemists. So it will help chemists to work very efficiently. We can say in the time you design, traditionally you design one route, now you can design more than 5 routes. And furthermore, it can show different methods which chemists may not be familiar with. For example, in this example, the key step is a reaction well known by chemists. You can see the ring close to give the imidazole structure. But ChemAIRS is able to propose other methods which could give the 2 functions in one reaction, and this will shorten 2 steps into 1 step. So you can see here it can construct the ring and in the same time add a bromide or iodide function on it. Sorry. Yeah. The second case is a target have different 3 purity centers, and we tried it with our chemists internally, but they failed to design a feasible route for this molecule. And so we just run ChemAIRS to see if it can give some good routes. And of course, it found a lot of routes. And we just evaluate the first routes, and we found both of them are quite feasible. For example, the first route tried to construct the chirality center, and the relative configuration are all correct. And the second route is even better. It starts with available chirality starting building block, and it the chirality center are brought to the final target by reactions. So here we are sure the chirality center could be correct, but as a chemist, they cannot know all these known building block or known molecules. So it's quite difficult to design a route like this. So that's why we see ChemAIRS can help to overcome difficult targets. And in the case 3, ChemAIRS can help to find a better route for known or unknown compounds. This molecule is a drug API, and it's already fabricated in large quantity. The synthesis route is already reported in literature. So we tried it in ChemAIRS, and ChemAIRS is able to find the same literature route. So this is the first thing. But furthermore, ChemAIRS find more new routes with different strategies. And we just checked them, and we found some of them have cheaper starting materials, and the steps are also shorter. For example, in the first route, the number of steps is similar to the literature route, but the starting material are cheaper. We check the price. And in the second route, it has 2 steps shorter than the literature route, and the starting material are also cheaper. And this could be a new route which could fabricate these products in a more economic way. And also there are other different strategies found, like the strategy 3. So even process chemists could be inspired and use ChemAIRS to find a lot of different strategies and even more economic route with less waste. So it's quite useful in this case. And in the case study 4, I have to show you if we make the use of internal ERN building block data, and it will change the way chemists work. For example, here you can, in the old way of designing a route, chemists first design the route, then they check if the building blocks are available. But with ChemAIRS, it's changed. The system will check each intermediate in the search, and so it will check a lot of chemistry space, and it also check in the ERN database and the building block database. And then it will be able to find routes like the first one. It finds a building block, and it can get to the target in a very short step. So this will make a very short route. And in other case, it will find an intermediate existing in ERN database, and then you will have a route which is much more feasible because it's already proved internally to get to the target. And this is often happen because in the company they do a lot of similar projects. So this will totally change the way of route generation, and it will be quite useful for chemists to find a better route. In the case study 5, just an example, chemists can also use ChemAIRS not in the route design, but to find optimize the reaction conditions. It's very practical. You just draw the reaction in the panel and click condition optimization. So not the first one, but the third option. And very quickly, ChemAIRS will show all available conditions to make this transformation. In principle, the same reaction conditions are merged. So you will not see a lot of same condition, but different conditions. And it will help chemists to quickly find the best one because we order the conditions by successful chance calculated by algorithm, which will consider the structure similarity, chemoselectivity, radioselectivity, and also the predicted yield. So this is very practical for the daily use. And thirdly, we have also developed other tools to accelerate the preclinical drug research. For example, we have assay score for one synthesis and process chemistry module. So for assay score, it's when you design a lot of molecules, you want to know which molecule is more easy to synthesize, so it will shorten the project and cost less. And this is very complex because currently we have some algorithm, but they are not quite good. The best algorithm should be an algorithm work out the synthesis route and then calculate the difficulty of synthesis based on the route. So that's why ChemAIRS can do it. It will calculate very fast the synthesis route of a molecule, and based on the number of steps or the complexity of the reactions, it will give a score from 1 to 5. And we just, to validate the accuracy of assay score, we compared the assay score of ChemAIRS with the assay score given by human, published in a publication of Merck. We find that generally AI can give a very similar score, which also given by human chemists. So we made a chart to compare. In this picture, we can find between the two blue lines, 86 of molecules. The human score and the ChemAIRS score are quite similar, so in this zone. And in some cases, we found also there are some points, especially in the red bottom corner, you find some points there. It's not too much, it could be 6%. Okay, no, 2% of molecules in this zone. And we check them, why there is a big difference between ChemAIRS and the human. And we found mainly because chemists do not know a building block exists. And from this building block, we can synthesize a complex structure into 1 or 2 steps. So human gave a very high complexity score on this molecule, but AI have the route and it tells the synthesis route is quite short, so the score is quite low. So in this case, we can say AI could perform equivalent to and even better to human chemists. Yeah, just to mention, this assay score work very fast. We can evaluate 100,000 molecules in 8 hours of calculation. And another tool is called forward synthesis because it's used to design a library of molecules. So sometimes we have a prodrug or a target, a hit or a lead, and then we want to know what kind of similar molecule we can synthesize using the same synthesis route and using all the building block we can brought in the market. And this is a tool made by Chemical.AI, and we can generate a lot of similar molecules, start from available building blocks or ERM building blocks, and using a similar route of synthesis and give a library. For example, we generate a library like this. You can see all molecules are quite similar, and they are all accessible by several steps of synthesis, the same route. And then chemists can calculate another scores and decide which molecule we want to make. So this is quite practical to design a new molecule. We have also a module called process chemistry. It's generally design routes like retrosynthesis, but chemists can add a lot of filter. For example, we do not want to use palladium catalyst because it's expensive, or we do not want to use reactions which is toxic or reagent which is quite expensive, etc. So this tool is quite advanced, and we also have a mind map presentation to show all the synthesis parts in the same picture, and the chemist can zoom in and zoom out to see the different important key intermediates or reactions or starting materials. And this is used to help process chemists to discover new strategies to make a known compound. Yeah. Thank you all, and I think this is all. Our site is www.chemical.AI, and now we have a free trial, so everyone can come to our website and just start your free trial for 3 months, so you can try easily. And thank you for your attention, and I hope our platform ChemAIRS can help more chemists in their daily work and help you to make more novel drugs. Okay, so if you have any question, you can ask me, or if you are interested, I can give a live demonstration of our product. Okay, I will, if you have any question on the slide.
Any question? Thanks for the presentation. I was wondering if you could show like a demo how to use the software or like how to use a package.
Okay,
yeah,
of course.
Yeah, thank you.
So yeah, thank you. I will share the software. Okay, so can you see my screen now? So our website is Chemical.AI, and we have a version, professional version. You need an account. If you are interested, you can ask us to have a trial account for 1 month, or if you just want to try, you can use our free trial version. It's mainly the same, but it's limited to search 10 search in a day. So I think it could be enough. So here is a panel. You can draw everything here. I will not draw. You can also paste from ChemDraw to paste the smells here, and the molecule will be drawn immediately. So we have retrosynthesis module, process chemistry, forward synthesis, acid core modules. So we just to show you the retrosynthesis module. For example, here we have a molecule. We can just draw this kind of molecule here, and we just click search. Generally, we have two parameters here. We can see how many roots I want. We can see 20, so it will stop like 20 roots. If we can put maximum to 100 roots, but I think it's already too much. And you can say how many time I can use. So maximum 60 minutes here. Of course, you can give us a longer time for 60 minutes if the molecule is really complex. And the search steps, I put 12 steps here. It's already enough, because with 12-step search, it can search to even 15 or 20 steps. And the risk level, generally we use low. If any case you have a very complex and novel structure, it found nothing, you can try to put to medium or high, but with this risk level, it can give some reaction which could fail. Yeah, and you can also limit the price of starting material. So here we put the maximum, but you can put, for example, 500, means the starting material will be cheaper. Okay, so for example, I just click search here, and it will create a task. So we can see there is a 0 here, means actually 0 root is found. Even 0 root found, we can click, and we can click manual search here. So you can, it's another model, means we can search manually step by step. So it will you can search each step, how many ways to cut this molecule, and you can just choose the molecule. Sorry, it's a bit long. Yeah, it's charging the molecule. Yeah, so you can check. For example, we want to divide this molecule into these 2 parts. You can click it and made this retrosynthesis manually. But this is not I want to show you. This is only when the molecule is too complex, but because generally it will find very fast routes. For example, here you can see a +9, which means it already find 12 routes here, and we can click this number and see all the routes it's already found. We can see the steps are different. Okay, so I just, for example, click the first one. Okay, so you can see the route already found. The purple color means these are predicted molecule and predicted reaction. And these green molecules are starting material or known molecules. You can even click here to see the price. So the molecule have, we have a database of different supplier. You can see the package size, purity, leading time, and the price. You can even have the purchase link here. You can have this. Case number, smells, informations. And you can see, yeah, this molecule is sensitive through this route. We can have a lot of reference below. It can tell you why we made this, because, for example, the first step, it's the amine group make a SN2 substitution on this bromide group, and in the reference, we can see also this is a similar reaction with a ring on the amino group and SN2 substitution. So the system is, when it did not find any exact match, it will find a most similar reaction, and to show you this reaction can work in the similar conditions. You can see here the condition, and also the link to the publication. You can have the DOI, and if you click DOI, it will lead you to this publication. We can also have ERN types. This means in our ERN, you have a great chance of success in this reaction. Okay, so if we come back, I think that the task is already finished. So it's netting. So we set to 20, so it will stop at 20 rows. Generally, it will search in 5 minutes. It will have a lot of routes. So 90% of molecule you can have result in 5 minutes. But for some really complex molecules, you need to search to 20 or more time. Okay. So this is a quick demonstration to how to search. Here we can also say which price we want to have, or supplier we want to filter, or even we can switch the presentation model from right to left, left to right. It depends on our preference. And we have this map mode. I just told you we can select all the routes and we click map mode. And if you show the target in the middle, and if we zoom out, I think we can see the molecule. Yeah, we can see the molecule. We can see how this molecule is synthesized by different strategy. Yeah. So in this case, we can study all the routes in the same picture. Even we can make some filter by yield or similarity. And we have a cost here. Just to say this route is expensive, starting material is expensive or cheaper. You can have an idea on it. You can have a limit, a total step number. So there are 6 steps, but we can also know how many prediction steps here, and the linear step, which means the project would be faster if the linear step is shorter. The difficulty is just a number. It's when it's a low number, means the difficulty is quite low. But it's we can see here that the difficulty are quite same. So but here it's higher. So maybe this route have more or less chance to succeed. Yeah, you can see it's longer. Generally, the system can find all strategies to synthesize a molecule. We can see all routes in the same picture, so you can just click one by one to see to find which one you would like to use. You can modify the route. For example, I can delete this molecule. I can do one-step synthesis to another molecule. For example, if we have intermediate and we want to see more strategies to make this intermediate, for example, this one, I think it's quite interesting, but I'm not sure this way is what I want to take. We can search route for this intermediate. We click here, and the system is have created another task here. Yeah, I think this one, for example, I can stop it if I think 20 routes is enough. And for this new molecule, new intermediate, we have we launched another search which will give different strategy to make this molecule. So this is quite interesting because we do a lot of work to remove duplicated routes. So if you search a target, you will have 20 routes, but besides that, for each intermediate, you can have 20 more routes. To see this, you need to search the intermediate again, and then you may find a quite useful route. Yeah, for example, here it's very short. It's even shorter than the route given before. Yeah. Okay. So I made a very quick demonstration. So do you have any question on it? Or if you have any molecule you want to try, you can tell me and I can draw it to try.
Great, thank you. So I think there is a question in Q&A. Maybe you can have a look and answer that question.
Yeah. What AI algorithm does Chemical.AI use? Is it supervised or unsupervised learning algorithm? Okay. Yeah, it's a very technical question. Actually, Chemical.AI use a different approach from purely deep learning, or so we cannot say it's a supervised or unsupervised learning algorithm. I think it's we use not quite much deep learning on this model, so we cannot say it. This algorithm is mainly based on I can see machine learning actually, and it's based on a mixture of human knowledge and data learning. So yeah, so that's my answer. It's not published in the paper, so yeah. Unfortunately, we are a company, so we didn't publish a lot. But maybe in the future we will publish something on that.
So Dr. Xiao, thank you for this nice presentation. So I have first is more like a clarification. So you mentioned there is a 3 months trial for your software. So I just want to know whether it's anywhere between May and July you can subscribe and then get 3 months from the starting date, or it's just limited to the 3 months period from May to July?
Yeah. When we say 3 months, it starts from May. So actually, they have 2 months left, but I think it's quite enough to test. You can just go to Chemical.AI, and in the home page, you will see a button "Try for free" here. And it will be lead to a register, and you just put your email with green code, username, password, and you can sign up. Then you will have a version, a free trial version. You can use, you can launch 10 search per day.
So this is a web-based search.
Yeah, it's web-based. Yeah. Yeah. For example, for the security, it's quite good. We made a lot of work on the encryption of the result, so no one is quite secured. But if you want to do some internal trail, for example, installation in your server, it's also possible. You can just contact us and we will make it possible.
Okay, I see. So there are two options. One is a web-based, and then also you can do local search.
Yes, yes, and
I see.
it's only possible to do ERN integration and in the local version. In the web-based version, you cannot upload your ERN data.
Okay, thank you.
Thank you.
I have a question. So I think there is some similar software, right, in the market. So what's your advantage in terms of, you know, I don't know, just, you know, maybe you can give some examples or details.
Yes. Yeah, we know there are a lot of different software. I just showed it in the demonstration, but I can show you again. Okay. Yeah, I didn't find it, maybe here. Okay. Yeah. So first, the performance is better. Our performance is better. This is tested by other group, other company, big pharma and CRO. But mainly difference is here. So they use mainly the pure data-driven approach or expert rule-based approach. So there are some limitation of this method. I just said, for example, the number of examples, number of data impact a lot on the data-driven approach, and it become a problem, and the black box problem. And also for the expert rule-based system, they have some different problem, like the bias, the experience is not quite exact as the data. So I can see our system in the term of performance. Performance, it means the feasibility of the route is quite higher. It's the most higher in current state. And also the speed is quite fast. Our system can give route in seconds to several minutes, and the rule-based system can only give in at least 20 minutes, for example. So I think this is a main difference. So the quality of the routes are different. And then we can say our system is already adapted by a lot of big pharma companies, and also they test a lot and give us a lot of feedbacks, and this made our system is quite easy to use. And this is another difference. Yeah, I don't know if it's correct answer, but as we made some benchmark internally, we found our system is really the first one who reached the level of experienced human chemist. So I think this is the biggest difference. Yeah. So I don't know if replied.
Thank you. Yeah.
Thank you.
So Dr. Xia, I have another question. So about the more like the IP protection, right? So you mentioned this is quite secure, but did you actually store the target molecule people submitted?
In the web version, yes, because the user can see all the tasks they searched. So it's for the user, but we do not see this because the information is encrypted, then stored, then put in the database. So in the database, we can see nothing, but the user can see this molecule. So technically, if we want, yes, it's possible to, it's there. But we will never let this happen in our system. And for local deployment, there is no problem because all the server, all data is inside your company. So it depends. If you have the ability to maintain a server internally, you can choose the local deployment. And if you are just a biotech, you have 2-3 person, you want to use the web version, it's okay. We can ensure the security of our server because it's quite secure in the cloud, with a lot of firewall or antivirus and other tools installed, and all the data is encrypted in the database, and we have a very limited access to this.
Okay, so maybe one more question. So we all understand that to make the retrosynthetic analytic software work or reliable, like it's very important to have a good source of data, right? So you must based on something, based on a huge set of data, and then the quality of the data actually is important. I just wonder to understand like whether like how do you get all those data, and then I don't know whether it's convenient for you to share. Like how do we know this is kind of you do all those things based on trustworthy source?
Yeah, we do work for the extraction of data for a long time. Since 10 years ago, we start this work, and we are able to extract chemical data from patents or literature, and then we do a lot of cleaning work on it to make sure we eliminate the poor quality data, and we just fix some errors in the data. So we can see our quality of data is quite good, and we also have a algorithm which can automatically learn from the good data, and just because statistically the good data have more accuracy. So that's very important. Or you will have poor data which will pollute the data poor. So I think algorithmically we extract data in a big quantity, then we clean it in a good way. Then when doing the search, we can just prevent the poor data to be seen by the user. So yeah, that's the process we do.
Yeah, that's interesting, right? So you mentioned you clean the data. So I just wonder how you do that. I mean, that may be your secret, but like you can just say as much as you can.
Yeah, it's using algorithm to do that. We cannot clean data by human, but if we see some error in data, we can make some algorithm to detect data, and then use algorithm to fix it automatically. So that's very interesting because it's also a lot of cumulative work because we do it for years. So it depends on each kind of error. So you cannot just clean all the error by one program. Yeah. It's our capability to do it.
Yeah, Dr. Xiang, another question in Q&A.
Yeah. With your limitation or your product. Basically, or actually, we are working with some ERN supplier, and it's not limited by ERN product because even the ERN, we do not have direct collaboration, but generally all ERN can export your data into a standard format like RDF file or JSON or XML file. Then we have an import module which can import this data into our system, and you can search in ERN. So it's no limited. Yeah, actually, we are working with Silicon on this, but any ERN we can do a manual import. Yeah, thank you. Okay. So does anyone have any questions?
So maybe one more question. So for because in San Diego we have many small biotech companies, and then I just want to maybe you can introduce to us like how do you have different maybe you have different like the business model to work with a biotech company, small biotech company versus a kind of big pharma. You have more flexible plan or anything like that. I just want you maybe just give us more information about that.
Okay. For biotech, in fact, we do not only provide the softwares. We have a laboratory to synthesis work, and they use not only the retrosynthetic tools but also automation modules, some machines to make the synthesis faster and more efficiency. So for biotech companies, you can contact us, and we can provide free for service synthesis or FT synthesis to give you your desired molecules in a quite efficient way. That's already proved by many our customers. So we can provide you the tools, and in the same time you can use our synthesis service to accelerate your project. It's our laboratory is in Shanghai.
Okay, thank you.
Thank you. Okay, so if you have any question, you can contact us by email or by WeChat. I can put my WeChat here. Yeah, I put my phone number. It's my WeChat number, so you can add me if you have any further question or demand for the trio or local deployment or other discussion. Thank you. So sorry, I didn't put it in everyone. Yeah, I put my WeChat number in the chat window. Okay. Thanks, everyone. I think it's all for today.
Yeah.
Yeah, thank you for the host.
Thank you.
Yeah, thank you. Okay. Have a nice evening. Bye-bye.
Thank you, Dr. Xia.
Yeah. Bye-bye.